Morning, everybody, and good afternoon, and thank you very much for joining the presentation today. I want to talk about flood resilience framework for the Caribbean region, a project that we have been working on, and I don't seem to be able to make this. Yeah, got it. This is a project that's funded by the New Frontiers in Research Fund from Canada. The lead principal investigator is from McGill. Myself and Dr. Adamowski are the nominated PIs from McGill. And we have co-PIs from the University of Louisiana, who are funded by the National Science Foundation, from the UK Centre for Environment and Hydrology, and Imperial College, London, funded by the UK Research and Innovation. So we have three funding agencies that have come together: the New Frontier Research Fund, the NSF, and UKRI, that responded to the call for proposals. This was a dedicated call for proposals to work on climate change in various parts of the South, and the region that we decided to develop a proposal on was from the Caribbean region, which I will obviously explain in the forthcoming slides why we selected this region. So we took our cue from this report that was generated by the World Bank, the European Union, and the Global Fund for Disaster Risk Reduction, a report entitled 360-Degree Resilience, a guide to prepare the Caribbean for a next generation of shocks. And it's quite a large report. I wouldn't have time to go through the whole report for you, so I've just highlighted a few slides. And what you'll notice in the slide is that and I should backtrack too, this report on 360-degree resilience was not only about floods, it dealt with all disasters, including earthquakes, hurricanes, tsunamis, and so on. But you'll see here, I picked out some of the slides that deal with flooding, and you'll see that in terms of Guyana, the poor populations who receive less than $5.50 a day, it's up to close to 40%. And then in the non-poor populations, it's around 35%. So it's a fairly significant proportion of people, especially in the poor populations, that are being affected by flooding, where there's more than 15 centimeters of tidal and riverine wave action. And then Suriname is the other country that stands out quite large as well in terms of being populations that are suffering from flooding. So if we look at this map of Guyana, you'll notice here that Georgetown, the capital city, is right on the coast with the Atlantic Ocean, and therefore the tidal influences are quite significant. And also there's riverine flooding as a result of wave action backing up into the rivers. And so you'll notice on the slides on the right-hand side, the red areas where the United Nations and the EU have plotted some of the areas that have been extensively affected by flooding. And to compound the situation, about 90% of the population of a country live along that coastline. So a lot of the economic activity, a lot of the commercial activity, banking, government offices, and so on, schools, hospitals, are located on this very tiny fringe along the coast, which at one time was all part of a wetland that was reclaimed by the Dutch and the British when they colonized the country. They built an extensive network of dikes and dams to be able to keep the flood water out. So the population lies, although it's a fairly large landmass, most of the population lie along that coastal area. And this is why the project is also focused in Guyana. You'll see the same thing here in Trinidad. You'll notice the areas that are prone to flooding shown in red here. And you'll see that part of that red area at the top of the island of Trinidad is where the capital city, Port of Spain, is located. And then down in the south, as you get to another major economic zone in Point Lisas, the San Fernando area, which is where the petrochemical industry is located. It's also subjected to enormous flooding. So there are many countries. I don't want to go through all of them, but there are something like 12, 13 countries in the Caribbean region that are affected by flooding in one way or another. And the impacts of sea level rise as a result of climate change have exacerbated the problems of flooding. That's why it's not uncommon if you look in the city of Georgetown, capital of Guyana, you'll see that there is flooding of the capital areas in the commercial districts, large residential areas that disrupts economic activity, disrupts schooling, and also hospitals, markets, food insecurity, water safety problems, waterborne diseases. There are all these outbreaks that are associated with flooding that makes it important to be able to develop techniques and a framework to deal with flood control. So very briefly, that Caribbean 360-degree report, there were several findings. But one of the principal findings there, number two, is that Caribbean countries are not prepared for the new challenges posed by climate change, compounded by the uncertainty of the future of tourism markets, a lack of fiscal space. And you'll see there that they have identified increasing government inefficiency would be required to improve investments, management, infrastructure in emergency situations. We need to empower households and the private sector to increase the fiscal space for them to help to strengthen the skills for resilience and improving access to finance to facilitate access to risk information and reducing future physical risk as a result of flooding. So these were some of the major factors that allowed us to push forward with the development of this proposal to the NRF, UKRI, and NSF. The objective of another project that was being conducted by the World Bank had three components to it as a result of severe flooding in the last 10, 15 years. And the World Bank has been putting money in to reducing flooding in the low-lying areas by providing risk reduction strategies, improvement of some of the dams, the reservoirs. Also important is the institutional strengthening for flood risk reduction. In some areas which they have not put as much effort as we are putting in now is the hydraulic and hydrologic modeling, specialized training, use of remote sensing tools. While the bank has done some of this, it's really left to us in our New Frontiers project to help to build some of the capacity there to support the work that the World Bank and other agencies are doing in the country. So as I said, it's a low-lying, flat coastal area. And there are a mixture of ways in which there is protection from floods. You can see at the top left hand, there are dikes, walls that have been built with boulder stone riprap to prevent overtopping of wave action. And to note that the waves are diurnal. It's a diurnal fluctuation, tidal fluctuation. There are 12 hours of the day when there's a neap tide, when tides are low, and you can drain by gravity, as shown by these sluices and gates at the bottom left-hand corner of the slides. And then when the tide rises, those gates are closed to prevent the intrusion of tidal water. But recently, especially over the last 15, 20 years, it has been found that some of these traditional methods of flood control have not been able to cope with the extent of flooding that we have witnessed as a result of climate change. So you'll notice on the right hand, there's been an increased amount of pumping stations that have been constructed, and especially pumping stations near to these outfalls by gravity that have been used to remove excess water. And the question becomes, which is one thing we would like to study, is how can we operate these pumping stations much more effectively through automation, digital controls, and so on, with different types of sensors of water levels to be able to trigger when the pumps should go on and off. Currently, there is a haphazard approach to rehabilitation and maintenance. It's very reactive. After floods have occurred, government comes in and starts to repair the retaining walls, do patchwork, build in better burns and boulders for riprap, but it's always in a very reactive way. None of this is being done proactively. There's not a scheme, a recognized scheme that is put in place to be able to deal with floods on a proactive basis. And this is something that exacerbates the flooding in the country. So the goal of this project is, and this was part of the call from the New Frontier Research Fund, is that it must be a co-designed, adaptive, co-management solution to the problem. This is not something where they would like to see international agencies just come in and develop a solution without getting inputs from the flood-affected communities. So we developed this framework which shows how we can work with the communities to, and I'll talk a bit more about this later on. This is some work that Professor Adamowski and Cody, our graduate student, is working on to look at bringing communities in to help to develop some of these strategies. And then how we can build capacity through better hydrologic data and flood mapping, how we can use computer models, and this approach of nature-based solutions as well, to be able to build resilience through a community-driven research agenda with iterative feedback. So one of the things that we're doing is getting feedback from the communities, and we're using that as we go further with our objectives for the project. So the major deliverables or outputs is this co-developed risk, hazard, and response model to serve effective communities, including the provision of communication products that the communities can uptake. We want to build capacity in the communities, government agencies, and local universities. And we also want to improve government policies and institutional frameworks for flood disaster risk management. So these are the three broad objectives, but there are many sub-objectives under these. Some of the methodologies that we are employing are flood forecast modeling, satellite monitoring of rainfall, watershed modeling, using very elaborate models that are suited to very flat, low-lying areas. Very difficult to model, and I'll talk a bit more about that. We're looking at these coastal dynamics and tidal modeling for the operation of sluices based on predictions to rainfall forecasting, as I mentioned before, and doing some more real-time water level measurements and data collection tools as part of our citizen science program. How do we empower the citizens in flood affected communities to help to collect data that can then go in to the hydromet agencies to beef up their data collection as well. And the smallholder engagement, community social dynamics, this is something that Professor Adamowski is bringing to the project. And then looking at the mapping of critical infrastructure, accessibility, and how do we build resilience to prevent that infrastructure from collapsing during times of floods. So we have about 8 tasks overall. And a big one here that I'd like to talk about today is this use of as much, and this is something that the New Frontiers Fund would like to see, is us using digital technologies that are freely available instead of proprietary information. Could we use satellite data that's currently available to do some inputs, provide inputs into some of our models so that we can get better water level data at selected points in communities and can help them to start to make this decisions about how to cope with floods, resilience to floods before the floods occur and disrupt their lives rather than after the fact, which is what is happening right now. So obviously we can't study the whole coastal area. We've picked out an area here that is where in region 4 of the country has 10 regions, and we've picked out the most important region because it comprises the capital cities, Georgetown, and a lot of communities that are very heavily populated along the coast. And interestingly enough, you'll notice here that behind the coastal area, or as part of the coastal area, there's this East Demerara Water Conservancy. And that conservancy was developed over 100 years ago to hold back flood waters from affecting the communities along the coast, to provide irrigation water to some of the estates and farmlands towards the coastal area, and also to provide a supply of drinking water. And so we've deliberately selected that area because that conservancy would play a very major role in any strategy and framework that we develop. And there's also quite a bit of data available from the conservancy that could be used for modeling. So it represents quite a nice area to study. And obviously in this project, whatever information and framework we can get for one region, we hope to replicate that through other regions, not just in Guyana, but in other countries in the region of the Caribbean region as well. So the East Demerara Water Conservancy, I've got the statistics here. I wouldn't go into it into detail, but it has a number of intake structures. As you can see here, there are 27 intake structures that are used to supply water to communities. And then there are some relief structures. There are 5 major relief structures that allow for drainage from the conservancy. And the picture at the bottom right-hand corner shows one of the major relief structures, the Hope Canal. And this is what drains quite a bit of water from that whole area of Region 4 and this conservancy, because what you'll see here, there's not a lot of water to play with in the conservancy for storage. There's only 4 feet really that's available. And so it's how do you regulate that water level there in the conservancy so as not to have overtopping of the embankment that would cause further flooding. So this is really very critical to the whole effort that we're doing on modeling, which I'll elaborate on a bit deeper. So you'll see Professor Adamowski and two of our colleagues from the UK as we did a tour of the conservancy. So let me spend some time, first of all, to show what we have been doing here at McGill and some work that one of my postdocs, Masood, working with myself and Dr. Adamowski have been doing on looking at some of the rainfall data. There's 6 stations that are located in Region 4. And we have been putting this data together, and Masood has been doing a terrific job in analyzing that data hydrologically and trying to tell what that data says. So he's done some statistical tests, and he's shown here that the region is statistically homogeneous. That allows us to have a regional frequency analysis model. And we have been looking at some other models, the Weibull distribution, the Wakeby distribution, to see if we can get better fits of some of the data. And the best fit is shown here by the Wakeby distribution. So from all of the analysis of the different models he's looked at, the Wakeby distribution gives the best fit of the rainfall data. So this is the first time that we want to leave products back in the region and in the countries that have never been looked at before. And this is one example of a very good product that we have developed on the fitting of rainfall data statistically. And then we've gone even further to develop these rainfall intensity frequency curves for each of the rainfall stations, given the number of years of data that we have. There have also been years of missing data, so we've had to take that into consideration. But as you can see, the 6 stations, we've plotted the rainfall depth duration frequency curves for all the stations with the Wakeby curve, and we now have a good product in terms of determining, for example, for the once in 200-year storm and the once in 100-year storm, you can see that we can expect to have about 200 millimeters of rainfall from those extreme events. So Masood has gone further with this, because what we wanted to do is to take some of this rainfall data and come up with a design storm, a synthetic design storm that we could start to put into our flood modeling. And again, looking at some of the stations individually, he has presented here some of the data that has been obtained on the intensity, duration, frequency curve, very similar for all of the 6 stations. So for different duration storms, different return periods, we've been able to go further, building these as products that can be left back into the country for design. And we don't want to design for today. We want to design for the future, taking climate change into account, obviously. And so Masood has done some good work in looking at how temperature and precipitation changes could take place to affect the precipitation going forward. And he's come up with this information that we have never thought about before, and certainly hasn't been thought about in the country. And that is these short duration convective storms that are occurring at temperatures greater than 25 degrees C, and looked into the literature and was able to come up with this hook effect that has been looked at by others, given that the location that we're working at is around the equator. It's not north of, in the northern regions nor the southern regions, but just as the equator. And so you have the effects of the intertropical convergence zone that have allowed for this hook effect to be considered in more detail. This is some of the early preliminary work. There's still a lot of work to do on this, but looking at what a synthetic design storm would look like, as you can see here, the present and the future in times of total amounts and then of rainfall and then peak amounts, you can see some slight increases, but this is very much early work and still much more investigation going on this. But already, based on the work that has been done here, we're coming up with some new numerical models on design storms that would bring tremendous inputs to the work that we're doing. Very briefly, I just want to talk about some of the work that's been done by our colleagues at the University of Louisiana. They have been working on the hydraulic floodplain modeling. As I said, this is a very flat area, hardly any hydraulic gradient from the upstream catchment area to the coast. And the coast lies about a meter below sea level on average. So this complicates the floodplain modeling. I'm only going to show you two slides, but my colleagues at Louisiana have done a year and a half of very extensive work trying to get these models, trying to get the model to work. They had to do a digital terrain model first, and then using some of the LiDAR data, being able to develop the mesh size or the grid size to run the HEC-RAS computer model. Very important work has been done here. And over the year and a half, they have been looking at all kinds of publicly available data from some of the reports done by previous consultants. And this is one of the problems with projects like these, is that you have so many data sources, but they don't match up. And so Professor Habib and his two colleagues have been spending a lot of time trying to get these models to match and to be able to run them without showing many of the problems that we would see when you run a model of this nature. You're obviously going to get problems with the water balance adding up. But some of the very, very preliminary results they have shown here is an initial assessment of the physical boundaries to ensure that there are no leaks or ingress of water into the coastal lowlands, to be able to get accurate predictions of flow modeling over this very flat coastal plain. So that's currently ongoing. As I said, a tremendous amount of work has been done on this, using both the tidal boundary as one boundary condition, and then the flows from the Demerara River and from the Haika River as the other two boundary conditions to be able to get the model to run. So that's very, very elaborate work. And I'm only able to show two of their slides, but very impressive what they have found so far. And then our colleagues from the UK Centre of Ecology and Hydrology have also been doing some other modeling, grid-to-grid modeling at 1 kilometer resolution over the whole country, and then narrowed it down to our study region here. And I mention this because it's very important from one standpoint, and that is the question of land use. Since the discovery of oil, it's one of the fastest growing oil economies in the world right now. The oil industry, oil and gas industry, has taken off in such large intensity that a lot of the land use is being converted into industrial areas, housing areas. And so there's less percolation of runoff water and much more now contributing to runoff. And one of the things that we hope to get out of this grid-to-grid modeling is what would happen if you change land use and you put more areas under things like wetlands, detention ponds, and storage reservoirs, and so on, to trap some of the runoff from the area. So that's where this work is leading to. Again, quite a bit of modeling has gone on there. When you look at one slide, it's very difficult to see how many, months of work have gone on here to get this to all work out. And of course, the data sources are also critical as well, trying to match them up. So another area that myself and Dr. Adamowski have been working on with one of our PhD students, Cody Danaher, is on the social side of things. From the standpoint of the New Frontiers Research Fund, these projects must be multidisciplinary. It's more than just the science and the engineering. It's how do you bring the social sciences, the humanities into account, especially as you're looking at bringing communities in to develop this flood risk framework. So Cody has been out to the region as he starts to build his systems dynamics model. And this is some of the findings that he has come up with. He visited two of our study regions, areas along the coast. And the two areas that he has studied, Cane Grove and Caledonia, you'll see the differences in land use, the impacts of flooding, and the facts that we need to understand much better some of these perceived flood characteristics. So that's what he's working on, looking more at this. And he will be going back to collect more data. As he points out, many government agencies are perceived as having a role, but the communication and coordination barriers between these agencies leaves a lot to be desired for the communities in the two regions. So his next step is to build the systems dynamic model. They've already collected quite a bit of data from the mapping exercise they've done, but now as they build a systems dynamic model, how can they look at incorporating different social ecological elements into the framework? The other area that is being studied is in Trinidad by our colleagues at the University of the West Indies, who are collaborators. And they have selected a basin in southern Trinidad, the South Oropouche River Basin, where there's quite a bit of instrumentation in the basin, a lot of flooding that takes place, primarily riverine flooding, some coastal flooding. But they have been looking at some of that data, and the plan is to use it for decision making, to do some of the similar hydrologic and hydraulic modeling that we've been doing, build capacity, and of course, build flood resilience. So, based on everything that we have talked about so far, one wonders, and this is something the New Frontiers Research Fund is trying to promote as well, is nature-based solutions. And so how can we incorporate things like mangroves, which are natural to the area, seagrass, reed beds that are also natural, and different reefs? How do we include all of that in trying to strengthen the resilience framework and build those structures in? So as I mentioned, there's mangrove protection. There's already some mangrove protection along the coast. You'll see in the bottom right hand some new plantations of new mangrove swamps that are being planted. The mangroves have been destroyed and used for firewood and so on to allow fishermen to get closer to the coast. But now trying to prevent that, trying to rebuild the mangroves is also part of something that we're looking at. This diagram at the top shows what the coastal defense looks like in about 430 kilometers along the Guyana coastline. You have this bitumen riprap at the bottom, then you have different sizes of stone riprap and then boulders. You have steel piles being driven to hold the revetment in and prevent it from moving. But this is quite costly to maintain. So, how long can we continue to do green infrastructure? and keep it sustainable in light of rising sea levels, intensified wave action. And then there's a large shift in foreshore because of the flows that come from the Amazon that flow northward up along the Guyana coast and causes this coastline to shift. So there are huge bathymetric and engineering challenges to keep this managed and properly maintained. And so myself and a former graduate student from Trinidad and Tobago, Christian Virgil, we looked at this, particularly in the case of Trinidad, of how we can reestablish these native seagrasses. And we published a paper in Blue-Green Systems on this to look at the rehabilitation and the effects it could have on trying to reduce flood damage. So these are some of the main highlights I wanted to present today. And I know, Carissa, we're probably getting close to time, and we want to leave some time for questions and discussion. So I'd be happy to answer any question. It's about 1.5 years of work that has gone into this project before, so I could only show you glimpses and snapshots. I can't show you every detail. And what I haven't shown here, but maybe Cody could talk a little bit about it, is that our colleagues from Imperial College, they're probably in the field right now, collecting data in Guyana, from what I understand, with the stakeholder communities as well. So I haven't presented any of that work here, but Imperial College has also quite a significant component here. And one of our colleagues in hydrology from Imperial College is working with us on setting up some of these sensor networks with low-cost sensors to develop a citizen science program, which again, I haven't got time to touch on today, but I'd be happy to talk about it should anyone have any questions. So I'll stop here, Carissa, and hand it over to you. Can you give me the question again?
How should financing tools be designed to help support these projects?
Well, it's a very good question. And, one of the common tools that's used for disasters, of course, is insurance policies. But no insurance company wants to take out policies, issue policies to help to prevent people from flood damage. For some floods, yes, minor floods, but these prolonged floods that last for several days, sometimes even weeks, it's very difficult to get policies for that, especially when there's a lot of loss, not just to property, but also to livestock, to crops, and so on. So this is one thing that we would like to investigate a bit deeper. We have some colleagues from the University of the West Indies in Trinidad and Tobago who work in the area of climate finance. And so we're hoping that once we get further along in the project and we can show with GIS tools and some of this modeling that we're currently doing, what's the potential damage to infrastructure, the water levels, and so on, that some of the climate finance and mechanisms and models they would be able to bring to bear on the development of new financing tools. But it's a very good question, and it's something in which the private sector, there is a call for not just the insurance companies, but because the private sector suffers from people who can't go to work, loss of jobs, loss of economic activity in the commercial sector, how do we get the private sector together with government to come together, NGOs, etc., to put together some climate finance and models? So that's to be investigated under the project.
Okay, perfect. So thank you everyone for attending. If there's no more questions, we will wrap this up for the day. So thank you again, and thank you for presenting. Greatly appreciated. Have a wonderful evening, everyone.
Thanks, everybody.